All right, everyone, good afternoon. Hi, Andrew. Are you able to see us or hear us? I think you probably can't see us.
Can't see you, but I can definitely hear you.
Okay, excellent. So thanks very much to Andrew Shao, who's at HPE, for interrupting his Canadian Thanksgiving. Andrew graciously agreed to talk today about vertical coordinates and arbitrary Lagrangian Eulerian systems in MOM6. So Andrew, take it away.
Great, thank you. Thanks, Dan. And hope everyone's enjoying the workshop. I was going through some of the slides earlier, and in the spirit of all of the slides that have been happening here, I'm going to try to do my best to give a primarily qualitative introduction to how the vertical coordinates work, and also this arbitrary Lagrangian Eulerian framework that part of MOM6 is built around. I'm trying to give you this just flavor of what, to get you that conceptual understanding. Of course, if you want to dive deeper into it, always happy to have a chat, or I think Alistair's also in the room, and he might know a thing or two about how this has all been put together and the history behind it. So just to kind of go through a brief 4 topics that I want to cover today. First is this question about why do we even care about the vertical coordinates, and motivate this discussion about, one, why we have so many different vertical coordinates, why we have to think about the complexities between these, and what that actually means for putting together a model, a GCM that can support a variety of vertical coordinates. The second part is this question that some people may not be aware of, especially now that the AL version or the AL mode of MOM6 is probably the one that's being used for most applications now, but also trying to just make this distinction between the layered isopycnal mode that MOM6 has, in addition to this AL vertical Lagrange remapping kind of scheme that we'll talk about here too. Then kind of do a little bit of a deeper dive into what the vertical regrid remapping scheme actually is, because it is very different from most other ocean models. So if people have experience with ROMs or NEMO or anything like that, any quasi-Eulerian type model, there's a real weirdness that kind of come into play. So want to just describe the algorithm itself, since it's not just it's not very straightforward. And lastly, because this is a tutorial, really want to kind of highlight some of the things and implications of what this regrid remap approach kind of has for both model users and also for developers of schemes within it, and or those kind of in the room who are working and thinking about regional configurations. Okay. So this is a plot that I recently made just to kind of really highlight what the difference is when we're trying to take a look at the ocean and trying to discretize it and define it by a vertical coordinate. So everything that you see here, right, is the same original set of observations taken in the upper that were taken along the line in the upper left. This is basically somewhere around 5 east, in the southern hemisphere. And going from -70 to 0. And so what we see here, right, is something, and what's plotted is salinity. And what we see here are the telltale signatures of things, of some of the salinity signals in the Atlantic basin. We have some very fresh Antarctic intermediate water around 50 south and around 1,000 meters. We have some hints that there might be a subsurface salinity maximum around 2,500 associated with AMOC. So if you take that and now you do what we kind of sort of do in most ocean models, which is to say, okay, let's take these observations and now discretize them according to a different type of vertical coordinate. So the Z-like coordinate, right? So these are all things like the original Z coordinates of the Bryan-Cox model, all the way up to things like the Z star and Z tilde methods, where you specify that the vertical coordinate just exists at pre-described layers. Now, if you interpolate onto this coordinate there, you get something that looks somewhat similar as what you see on the left, right, in the top left observations. But you start smoothing some things out a little bit, right? So by binning this up and discretizing the ocean, you actually start losing some of the underlying fine scale information. So for example, like as opposed to the observations where you can see the subsurface salinity maximum associated with AMOC, it kind of sort of gets a little bit more smeared out, and it's not as clear where that actually exists in the Z-like coordinate. So similarly, you can also do something where you divide up the ocean into isopycnal layers, right? So your surfaces of constant density, the interfaces here are the surfaces of constant density. the layers in between are somewhere in between the interfaces. And what you see here, right, is that, again, you get this different ordering of the layers. But unlike the Z-like coordinate, right, you have, there is no specific depth that the isopycnal exists at that's universal across the entire model, or this transect here, right? You have different thicknesses associated with isopycnals of different ones. They are not uniformly distributed. They're not they're not distributed uniformly in the vertical. And so there's a lot more structure in terms of what the layers actually look like as opposed to the Z-like one. And again, right, everything that's on an isopycnal layer, bounded by those black lines, also tends to smooth things out. So again, very much like the Z-like coordinate, you maybe don't get this very strong kind of like intrusion that you kind of see coming from the north, but you get some semblance of, okay, here's a layer and here's the thickness of the isopycnal and how it actually changes over the course of the domain. And then lastly, on the bottom right hand is the terrain following coordinates. So basically, these are always, the levels here are prescribed as just some fraction of the total column depth. And what this essentially does, right, is very, very carefully maps the topography itself, right? So the model levels themselves are primarily controlled by the shape of the bottom bathymetry. It has some similarities to what a Z-like coordinate does in terms of the numerics of it. There's some things around it that we won't necessarily dig into, but Alistair already covered in some of the dynamic core discussions. But this is how you basically, this is how the ocean models see the ocean, right? So each of these three different coordinate systems are displaying and can represent the system in a bit of a way. However, they each kind of basically put a lens in front of reality when you're talking about modeling. All right, one of the key motivations when we're choosing a vertical coordinate is that we really want to reduce the spurious dipycnal mixing, right? So we know from a lot of theory that and observations that the oceanic flow mainly goes along isentropic surfaces. So in the ocean, right, these are, well, you say isopycnal. If you want to be super specific, we'll use isoneutral, and we'll be a little sloppy today, where we'll just assume that isopycnal and isoneutral are the same thing. We know that the actual vertical mixing in the ocean is quite weak, right? There's good old Monk and Wunsch papers showing that it's probably around 10 to the power -5, 10 to the power -6 to maintain the abyssal circulation, which is very small and is only a couple of orders of magnitude above the molecular mixing. So this is different than it is in the horizontal, right, where the actual turbulent motions are actually many, many orders of magnitude higher than they are than the background, the background molecular mixing. Two sources of this numerical mixing. One is that when we derive these equations that the algorithms actually solve the equations of motion, those approximations often can lead to basically terms that look like mixing. The second source of it is the fact that model surfaces are often unaligned with isopycnal mixing. So if you see on the right-hand graph right there, right, you can see that if you are just doing along a z-coordinate advection, then you're going to cross an isopycnal surface, and that by necessity is a form of dipycnal mixing because you're moving water across an isopycnal. Some higher order schemes, so like very high order accuracy schemes, can help address one, but the vertical coordinate really is one of the key ingredients to actually address two. So just to show that this matters, this is the OM4, GFDL's OM4 paper, where they, same exact model configuration, but compared essentially their hybrid coordinate model, which is Z-like near the surface, but isopycnic in the interior, and just compared what the vertically average or horizontally average vertical profile temperature looked like as the model evolved. So on the left-hand side, you see that the hybrid coordinate, it essentially stayed pretty, the drift is very small. The potential temperature does not change that much over time, but the Z coordinate model definitely, especially in the within the thermocline, around the 500 meter, 1,000 meter layer, has a substantial drift associated with it, which is somewhat characteristic or is emblematic of this type of vertical mixing that might be the spurious numerical mixing that might be induced due to the choice of the coordinate itself. You can see this even more you can see this in idealized cases as well. So if you look at the bottom right-hand corner, this is essentially just a wave that's passing through this domain, and there's a sharp interface near the center of the domain, and you compare what an isopycnal-like model does on the left-hand side and the Z-like coordinate that's been refined near the center domain on the right-hand side. And as you can see, the comparison around the same amount of time, that sharp interface is diffusing. And again, that's very, very similar and consistent with the type of numerical mixing that can be induced by a Z-coordinate model, because you're vecting across surfaces and or these lower order accuracy schemes that can induce some numerical mixing as well. Okay, so hopefully that gives you a reason and an excuse, if you haven't already been thinking about the fact that vertical coordinates are important and that they actually have knock-on effects to some of the science that we do with these models. And now I really want to jump into this description before jumping into the full ALE portion of it, kind of this divide that exists in MOM6 between the layered isopycnal mode and the ALE mode. Again, don't really want to go into the dynamics of it, but I'm also going to use this as a way to review some of the formulation and motivate why MOM6 is the way that it is. So I know that Alistair showed a timeline of MOM6 and its evolution over time, and I decided that I was going to do that and actually take the primordial MOM6 commit. Right. So the joke that I was told when I joined GFDL as a postdoc in 2016 was that MOM6 has a heart of gold. And there's a really good reason for that, which we'll get into in this section as well. But the very first commit, right, is literally just you take this tag from gold, and then you rename gold to MOM6, right, or to MOM in a lot of these places. And just because I was looking at the Git log, if anybody's curious, this is the second MOM6 commit. So, you know, I don't know who this Alistair Adcroft character is, but apparently he needs to learn how to use Git. But he did do the right thing. It did not overwrite history and just added another commit onto it, despite making a mistake on the git commit. Okay, so why is MOM6 actually based on gold? So Alistair showed some of the governing equations and the vertical discretization on yesterday. And so that is somewhat repeated here as well. So gold, the name derives from the general ocean layer dynamics model. It's formulated in general vertical coordinates, right, which are the equations of which are shown on the right-hand side. Essentially stacked shallow water equations. It was used by GFDL and CMIP 5 in the ESM2G version of the coupled climate model that GFDL released. And really, it fundamentally has a Lagrangian representation of the way that things evolved. One of the big things about these types of, especially when these layered equations are explicitly made as dipycnal models, or as isopycnal layers, is that you can actually directly control the dipycnal mixing, right? Because the only exchanges across the layers can be kind of put into play. There is no advection across the surfaces. All advection happens along the layer, and so, you know, any mistakes in the numerics basically just look like a little bit of extra along isopycnal mixing. And as Bob told me at some point back in, again, 2016, is like, why do you actually need an accurate advection scheme? It's an isopycnal model, and that's kind of sort of holds true because, again, any numerical errors that would lead to extra mixing happen along an isopycnal surface and are likely smaller than potentially the parameterized mixing. There is no continuous boundary layer representation. It is all bulk mix layer. You could take advantage of the fact that these are all isopycnal layers, so it simplifies the pressure gradient calculation, again, as Alistair mentioned yesterday, and that, again, the advection and the diffusion operate along isopycnals without any changes. Right? So this is a difference between virtually any other type of coordinate model where you have to do something special if you want to diffuse along isopycnal or isoneutral surfaces in the interior. Okay. So just to dive a little bit deeper into this, right? So we really want to focus on the fact that these are the layers in gold and MOM6 evolve in a Lagrangian way. So what happens? What does this actually mean? We'll throw up some equations here right now just to help explain what's going on. These again are the equations of motions in a general vertical coordinate. If you see this term ZR theta or ZR dot anywhere, this is the motion of the grid relative, or motion of the coordinate relative to the grid. And if you take the Lagrangian limit where R dot goes to 0, then you get to eliminate a bunch of terms, right? And so you get things that are a little bit interesting and maybe slightly different than the equations that we were taught in GFD. But they end up being something like the thickness weighted equations for mass, temperature, and salinity, right? So continuity, instead of just being del dot u dt, du dt equals del dot u, now you get a thickness term in here. And so you can see that there is, you're conserving mass instead. Likewise, instead of just conserving just temperature directly, really what you're doing is you're conserving a thickness, the temperature times the thickness of it. And so there is this discrete heat content that we're explicitly trying to conserve here. Okay, so what does that actually mean? So let's kind of go through a cartoon of this. And so we're just going to set up this really kind of, again, cartoon way of saying, we'll specify the velocities in some of these layers and just see how they evolve in time if we're evolving the layers in Lagrangian way. So at t equals 0, we have 3 different layers of the model, 3 different columns. And what I'm showing here in the coloring is basically the tracer. You think of it as an analog for some tracer value, right? Where the darker colors is a higher concentration of some tracer. So at time equals 0, this is the setup. And then you take one time step, right? And so what ends up happening? Okay, well, you're going to transport some mass out of the top layer, and then you're going to get some mass convergence in the bottom layer in that center column there, right? In this particular case, you're still only advecting along a given layer of the model. So there is no change in the tracer concentration. There's change in tracer content, but not concentration, right? And because these layers are only ever exchanging with their adjacent neighbors, there is no mixing across the surfaces here. So that's kind of what's illustrated here in the top right one here, t equals 1, right? So that bottom layer has inflated a little bit. The tracer concentration has not changed. And that top layer in the center column has gotten a little bit smaller. Yeah, you can kind of keep on doing this for a couple of times, right? And again, what happens here is that if you have this prescribed velocity here and this just prescribed kind of the resultant mass transport, eventually you get to a point in the model which looks something like that bottom right-hand corner, right? So you basically exhausted all the mass in the lower layers on the left and the right columns. They've all kind of been just transported into the center one. And similarly, the top layer of the middle column has essentially given its mass towards the towards neighbors columns. So now we got this really weird kind of thing where, again, we started with a perfectly uniform grid, you know, in the vertical, all the boxes were equal, but now we've got this little weird situation where the layers have evolved in a Lagrangian way, and so the thicknesses have changed. Again, you know, you might be tempted to think in the bottom right-hand corner that those 2 top boxes that you can kind of sort of see there, the ones that have like mass in them, might exchange with each other, but no, they don't, right? Because again, despite the fact that that top layer has quote unquote vanished, it still is connected in kind of the discretizations, the horizontal discretization with its neighbors, and similarly on the bottom. So we call this kind of like the vanishing, we call this the vanishing layer because at some point this layer effectively does not exist in terms of impacting the physics, but it does impact it in terms of the numerics itself, and we have to account for these kinds of things. Oops. Oops. Okay, so the important takeaways, right? Exactly what I just said. Tracer concentration has not changed in any cell, right? The extensive quantities, though, right? The ones that are thickness associated with the thickness have changed, right? So we have different amounts of tracer content. If we calculate the column tracer content, we will have calculated a difference in that from the time t equals 0. And then, yeah, just to reemphasize that, yes, the horizontal calculations are always done along a layer. So despite the fact that the top layer in the central kernel has vanished, it still does play a part in the calculation of quantities when you're doing horizontal calculations. One of the things too is, and this is an important thing and a part of the motivation for the ALE routines, and then also some of the original formulation in gold, is that despite the fact that these layers have vanished, because they still exist and they can still exchange with other layers, there's the possibility that they can be quote unquote reinflated later, right? So they might have effectively disappeared, but if you just get a little bit more mass into it, either because you transferred mass from the bottom, the layer below, or the layers to the side, then you can actually reinflate these layers and they can exist again. And so it's a very natural way of representing this wetting and drying process, where you can have places where it dries out, so effectively all the layers vanish, but later on, if there's an influx of something, then you can actually reinflate them. Okay, so going into this, well, let's go a little bit, zoom down into it a little bit. But before I do that, I just want to stop and see if there's any questions that anybody in the audience might have. Again, if you're coming from a purely quasi-Eulerian type model, this is a very strange thing to think about, right? What it essentially says is that at any given time in the model, instead of guaranteeing that you know exactly what the thickness of the layer is, or pretty close to what the thickness of a layer is, it can kind of be whatever the physics or whatever the dynamics want it to be. So just want to take a couple of breaths and see if there's any questions that people have before continuing on.
Questions for Andrew? I'll call on people because he can't see us.
I'll let you cue me ahead if nobody has a question yet.
Okay, yeah, they all seem very comfortable with having their lives turned upside down. So.
Okay, great. Okay, so now we're going to get into the specifics of what we mean by the regrid remap, right? So actually, before we do that, right? So there's this question, and the original formulation of gold allowed you to kind of do this diapicnal mass transport, and very naturally allowed for vanishing layers. But there's some particular assumptions that you can make that make it a little bit easier. What the motivation for the regrid remap portion of ALE was that now we really want to think about kind of arbitrary coordinates, right? An truly arbitrary general vertical coordinate in which to break apart this idea that layers might vanish, they might come into play, how they define it, how they evolve in a Lagrangian way over the course of the time step, can all kind of be taken care of at once. This problem of vanishing layers especially is one that is very challenging for traditional numerical advection schemes, because they really do not like if you are like trying to transport things across a massless layer, a very thin vanished layer. There's all sorts of techniques that have tried to do things like this, but they end up either being slightly diffusive. They might have to recompute things like what is the connectivity of the actual vertical column, and it just becomes a real kind of challenge from both the numerics and implementation side. Okay, so let's talk about the regrid remap question again. So we're starting with the end state of that Lagrangian evolved place where we've got some layers that have deflated and some that have vanished. And now the question is that we want to map this model state onto a new grid, right? And so we're going to introduce a couple of terms here to kind of figure out and motivate why we have split this algorithm up in kind of two steps. One, regridding is the process of finding the interfaces of a new vertical grid. So if you see on the right-hand side, right, that is the final state after 3 time steps. And maybe we want to say that we want to remap the model state. We want to get what the model state is on the original grid, which was this kind of equally distributed layers and 3 different layers. So the regridding in this particular case would be is somewhat trivial. It's essentially saying, okay, put a layer at, I don't know, 10 meters and 20 meters, right? There's interfaces at 0, 10, 20, and 30 meters. And that gives you kind of this uniform vertical grid. Of course, if you have a grid that is state dependent, so for example, if you're using an isopycnal grid, where your interfaces are defined based on a density value, which obviously then depends on the temperature and salinity, this becomes a non-trivial calculation. And in fact, even for the Z star, you still need to do a little futzing with it because the dilation of the barotropic motion of the water column due to barotropic motion actually means that you have to do a little bit of adjustment on the Z star and the sigma coordinate grids. Okay, so that's the regridding problem, right? Like just essentially, how do you calculate the new grid? Where should the interfaces of the new grid go? Now, the remapping aspect of it is now the problem of how do you go from a state like that top panel to the new grid? We'll kind of go into it a little bit, but there's a couple of real key things that we really want to make sure, especially because we're in the business climate. Is one, we definitely want to conserve total tracer content, right? So that is salt and that's heat, right? There is no statement of conservation of temperature in our equations of motion. It's all a conservation of heat or salt, right? These integrated quantities. So we would like to say that if we calculate the total content, especially if we're only thinking about the vertical now, we would like to preserve the total tracer content in the vertical when we column integrate. So that's one requirement. Two, we should not make any new extrema, right? And so that means that there should not be a new maximum that gets created or a new minimum that gets created, right? So for example, especially for tracers like salinity, which are always positive quantities, right? It makes zero sense, and it would be very not undesirable if our numerical algorithm gave us something like -5, salinity units, right? That's just, that makes absolutely no sense. And then we also prefer this numerical scheme that has no minimum time step, which is essentially one of these problems that traditional numerical schemes that look at this kind of problem actually do have. And just a quick diversion, this particular way that MOM6 solved it is a class, belongs to a class of arbitrary Lagrangian Euler methods. Really, very, very simplistically, any ALE scheme is one where the underlying grid is kind of allowed to change, and on which the motions of the fluid and the motions of the grid are kind of somewhat accounted for. Right. One thing that most of these algorithms that implement an ALE-like derivation can do is that they can recover the pure Lagrangian or the pure Eulerian limit. So either the grid is always fixed or the grid always evolves in time. Steve, Alistair, and Bob wrote a really, really nice paper that kind of outlines a lot of this. And in that paper, they referred to the MOM6 algorithm as the vertical Lagrangian remap. In MOM6, we kind of use the two terms interchangeably, AL and V, and I don't think vertical Lagrangian remap actually shows up anywhere in the source code itself. So if you're staring at source code or you're staring at the MOM parameter doc.all, all of these things will be kind of associated with this ALE aspect of it. But just to let you know, especially for those folks coming from different modeling systems or who work with a variety of them, just because a model claims that it's ALE, it does not, or just because a model says that it's ALE does not mean it's the same flavor of ALE as the MOM6 one. Okay, so step one. So step one in the remapping process. So the regridding process, like I said, is primarily a problem in understanding how you calculate the new grid given the model state. The remapping problem, though, has two steps in and of itself. So before we kind of jump into the whole reconstruction aspect of it, I'm going to just take a quick break and remind everyone, right, because this is a finite model, all the tracer quantities are volume and thickness average. We have no idea what the tracer profile looks like within a layer. All that we know is that from one layer to the next, the tracer concentration goes from one number to another number. Now, this is essentially the same as a piecewise constant representation of the interior. So that's what the leftmost panel here is essentially saying, right? So within a layer, without making any additional assumptions, this is what the tracer profile actually looks like. Now, if anyone has ever taken and plotted anything from, an Argo flow, this is not quite the way that the ocean works. The ocean is actually fairly smooth. And what this type of system actually represents is kind of sort of a system that has a lot of hydraulic shocks in it, right? Each and every one of these layers is a hydraulic shock. And if you do a scheme, if you do numerical schemes for this, they end up being and apply them somewhat naively, they end up giving you a very diffusive system. And so you essentially get, a lot of numerically induced mixing. So the approach that Bleck took in 2002 was essentially, and that has since been advanced and modified in MOM6, is to borrow the reconstruction portion of the invection schemes. Right, so invection schemes in general have mostly been designed to say, like, okay, well, let's assume that this fluid is not just a series of hydraulic shocks. Let's assume that there is some smoothness, some underlying subgrid scale profile that exists. Polynomials are great for this because we can understand and constrain their behaviors really easily. So it's one of the reasons why even if you go look back into papers, like some classic papers, they all use polynomials. So first you have to assume a basis. So you can assume a basis like a linear function. We can just say, hey, we think that there's a linear profile that goes underneath this. Or you can use go to higher order polynomials, right? You can use parabolas, you can use quartics. You can kind of go as high as you want, though there are complications that kind of come into play the higher order that you get. So to constrain these polynomials, then you need to interpolate in some way, or in some way estimate what the values at the edges are, right? So what I mean by edge values, and you'll see this basically in the code everywhere, is what, given this piecewise constant representation, or given a tracer profile at the interfaces, what should the tracer value actually be? What should the tracer concentration value actually be? And then from that, you can apply a number of different constraints, whether they're slope constraints, whether they're matching constraints or whatnot, and then actually constrain and come up and derive what the polynomial representation actually is. There's explicit things in the formulation and or the checking of things where we ensure that the value lies between a local minimum or a maximum, and or that we apply slope limiters to ensure that they're always that the tracer profile is always increasing, decreasing, and essentially just satisfy a total variation diminishing constraint, which essentially means that it's a monotonicity constraint. What the result of this reconstruction process actually is then a piecewise polynomial representation of a tracer profile. And so by what I mean by this capital sign, the Z, right? So Z here is a depth, right? It's a depth in the model itself. And so between certain parts of the vertical column, we have different polynomial representations. So for example, in the top layer, which might be bounded by the surface, and then something a little bit deeper, you're going to use one particular polynomial there. If you're going to do it, if the Z point, if the depth point lies within a different layer, then you just kind of look up what that polynomial reconstruction is there and then evaluate that polynomial. So instead of having this like one continuous kind of idea of like what the model actually looks like, we have these kinds of things which are piecewise, and because they're piecewise and due to the constraints there, they're often not continuous, right? So the piecewise constant is obviously discontinuous, kind of somewhat trivially, but even for like piecewise linear ones, you can't actually satisfy all these constraints all the time and still have a continuous looking profile. And so that's why you start seeing these breaks between the layers where it's like, okay, there's lines, but even at the same interface, it's a dual valued function, right? So for example, at the, I think that might be the 90 meter one, so just above the 100-ish kind of one, you see a break. Even though the two lines are exactly at the same depth, it's a multi-valued function. And so this is just a simple result of these constraints that we have. Again, moving to a higher order polynomial can kind of alleviate this discontinuity. So as you see, like going from PLM to a PPM of the exact same original tracer profile, you get functions that are much more closely, that more continuous, more errors where it is continuous, but it is again piecewise continuous. All right, so that's step one, right? Is this whole mechanism and whole parts of the code base which are just solely devoted to calculating these edge values and applying all these constraints to actually come up with the polynomial reconstruction. Okay, so then how do we actually remap the state? The easiest way to explain this is the remap by projection method, which was one of the original ways that was implemented in MOM6, but does not exist anymore for good reasons. And so I'm going to talk you through this using this because it's the easiest way, because it does involve an intermediate step. but it hopefully gives you the idea of what's actually going to go on here. So again, remember the fact that our goal is to try to conserve the tracer content, not the tracer value here. So to try to evaluate the tracer content of the new cell, you first identify the polynomial in the source grid, right? So you're saying, okay, I have a cell, these are the polynomials from the original grid that span this here. So if you're looking at the k=1 layer here, this layer is exactly the same on the old grid and the new grid. So it's a very trivial thing where we can just say, great, we've got one polynomial, we just integrate across this polynomial and multiply it by the layer thickness, right, to get the tracer content. And so one thing here to note is that in MOM6, it's implemented such that these polynomial reconstructions always go from 0 to 1. So kind of at the top, the shallowest interface is 0, the deepest interface is 1, and you integrate down when you're doing these things. In order to do this integral in a non-trivial way, so like when a part of the polynomial reconstruction doesn't just map directly one-to-one onto something in the current grid, now we have to find the average value of the polynomial, right? So this is the equivalent essentially like, coming up with a finite volume representation of what it looks like, right? What is the average of the tracer over some domain of this? So we're kind of going back from the subgrid scale, understanding and profile to something that we're averaging over a finite volume or a finite thickness in this case, because it's only in one dimension. So trivial calculus there. The average of a function is just 1 over the limits of the integration multiplied by the definite integral of those two. So you then, when you do this, like in k=2=3, so on the right-hand side, we've got this nice big thick layer that actually encompasses 2 of the original grid, right? So what do you do there? Again, multiply by the thickness of the original layer, multiply it by the integral of the polynomial reconstruction, and then you just sum those two things up. And so now you have the tracer content on the new grid. Now, a lot of things don't actually take heat, right? So for example, even the equation of state wants temperature. So you can convert it back to your concentration simply by dividing by the thickness of the new layer. So, to go from that tracer content, just divide by this new big thickness there. Okay, now for the slightly more complicated case, right, where you've got one original source cell and 2 new cells, 2 new layers on the new grid that span that, what do you do now, right? Well, you apply those same formula. They're slightly more complicated looking, but in this particular case, we say, let's multiply the thickness of the layer here divided by the limits of integration. So we're going from 0 to 0.6. Integrate that polynomial from 0 to 0.6 again there, and then this is essentially what you get, right? You get the thickness, you get the average of that polynomial over this little span, and you multiply by the thickness again, and you get a tracer content associated with that. And then down here, similarly, right, it's very similar to the k=3 case, except instead of 0.4 that you're dividing, instead of integrating from 0 to 0.6, you integrate from 0.6 to 1. And then 1 minus 0.6 is that, and then you're still integrating over the same polynomial. So I'm going to pause here real quick because this is somewhat confusing and a very different way of doing kind of like, I don't know, anything related to the vertical, but just want to make sure that people understand that, yeah, this is how we use the polynomial reconstructions to actually calculate and move things from one grid to another. If I don't hear anything in 2 breaths, I'll just continue on.
Pause for questions. All right.
Okay. So what actually in MOM6 is a slight change in this. So this actually borrows some, is philosophically similar to something that happens actually in the coupler, in the GFTL coupler, where you essentially do a superposition of 2 grids, and then you calculate intermediate quantities and then aggregate those quantities onto the new grid. So what this allows you to do is kind of ensure that things conserve somewhat exactly or down to floating point precision, and gives you a kind of a different representation, a little bit of flexibility in terms of how you aggregate these things. So exactly the same approach, with the only difference that instead of directly mapping from the current grid to whatever your new grid is that you make this new grid that is essentially the superposition of both those grids. So that's what these kind of blue dashed lines here are, right? You've taken every layer in the new or interface in the new grid and the old grid and just created this one. So instead of having 4 layers, we now have 5 layers in this particular case. In general, this is kind of a combination. This is almost you almost always get a grid when you do this that's twice the size, basically, because the only reason why it's only an additional one here is because there's so many layers that line up here. So just think about this. Don't worry about it too much, but that's the main thing that you should note here, right? Is that it's unless the grids overlap exactly, you will always get the subgrid to actually be much finer than either the new grid or the old grid. Okay, so you do essentially that process that we talked about in this by projection approach, right? Where you go through and you integrate polynomials and stuff like that. The main difference here is that in order to conserve exactly, you go through and you look at every single subcell, and then you say, like, okay, in the source cell, which of these things has actually, which one of these things is the largest, thickest subcell? So if you're looking here, right, we've gone through all these things, and now we've split this up. This part of it here, where we got this sigma 4 star, sigma 5 star, or phi 4 star, phi 5 star. And so these are 2 of the sublayers in the initial one. Now we're going to modify this so that the thickest cell in the destination cell that still maps onto this one here, that overlaps the most here, is not actually the direct integral formulation. What it actually is the difference between the tracer content of the source cell minus the sum of every other layer that actually connects to that source cell there, right? So in this particular way, we are ensuring direct conservation of the total tracer content when you map from one source cell to another one. One of the things I love about reading some of the comments sometimes is that there are some of these tidbits. So if anybody wants to see, this is the commit where I think it was Alistair who wrote the AKA a genius algorithm for active conservation. But this is essentially the way that we make sure that we conserve tracer column inventory, tracer column content exactly when we do this regrid remap. So one also caveat here too, even though we're using these very high order remapping schemes and like regridding remapping schemes, they are still not perfect. They will still have issues. They still induce some kind of numerical error. So you can't just kind of willy-nilly just regrid remap whenever you want without making the solution more and more diffuse due to this kind of the induced numerical mixing. So one of the things, and I'll touch upon it a little briefly, is that you don't actually want to regrid remap outside of the main ALE step. Okay, so kind of moving on in the last few minutes, consequences for users and developers. So let's go through and just say what actually happens over the course of a MOM6 ALE time step. You have some initial state, you've got some Lagrangian motion that comes through, and the layers evolve in time. You calculate a new grid, you remap onto that new grid, and then you get a new state, right? So as you can see in this figure, this is taken from that Griffiths et al. Paper. You see that the tracer content has actually changed, right? As a function of Z, it is no longer just this nice, like uniformly homogeneous tracer concentration, but it actually retains the imprint of that Lagrangian motion that had happened, even though it's on a new state. Real key things to note: there's never vertical velocity as computed. You can try to infer it, and we have made many missteps. I have made many missteps in trying to do that. It is a non-trivial calculation to how to do this, because W just doesn't exist anywhere. Another big caveat: the grid is only guaranteed to be the target coordinate immediately after the remap step, because there's a variety of processes that can change the layer thickness, right? So especially in grids that are TNS, that depend on TNS, right? Anything that changes temperature and salinity can actually technically change or does actually change the density. And so even though you say, well, my target grid is continuous isopycnal, therefore I can always assume that my layer dynamics are always isopycnal, that's simply not true, except right after that grid remap step. And again, there's some things that this impacts. So, some things that we don't really, that kind of arise out of this is that we then also have to make sure that our schemes are robust to kind of these changes and this potential vanishing of layers in between steps. So for example, for freshwater boundary fluxes, if they go into the ocean, we always just apply a flux to the top layer. But when we take out, for example, evaporation or during ice formation, right, that flux is actually taken first from the top, but then we actually have to progressively go down in the case that there's more thickness flux that's implied from interior layers. Similarly for geothermal heating, right, like maybe we think if we're in a Z coordinate model that the bottom layer is 1,000 meters thick, how can we possibly ever dump anything like that, spread the geothermal heating over anything resembling that? Well, that doesn't really apply because the bottom layer might actually be this vanished layer. It might be that the bottom 20 layers are all vanished, right? So we now have to think about how we actually are distributing this all in the bottom or along the bottom and can maybe span all the layers. Really briefly, I don't want to go into the slide too much. This is mainly for everyone's reference, but there's essentially 6 types of vertical coordinates in MOM6 as of now. The Z-like one, which is often the reasonable default choice for folks who are doing regional modeling, since it's, at least it gives you something and there's not much tuning that's required for that. There's the terrain following ones that are sigma coordinates, so for folks coming from things like ROMs. The HICOM-like one is this blending between a Z-like coordinate near the surface, and then transitioning into an isopycnic-like interior. That requires a lot of tuning. And so for something like a coastal one, you can't, for a coastal application, or even like a regional model, you can't necessarily just take the current default configuration for this hybrid coordinate and expect it to work optimally, right? You really need to define some of these really key metrics, like, okay, which isopycnals do you want to represent and what are their outcrop levels there, and like what aspects of the stratification are you trying to target. So there's a lot of hand tuning and a lot of trial error that goes into that. There's a didactic coordinate that's being worked on by folks, especially of Australia. And so this is essentially trying to borrow ideas where you can say, like, okay, can we concentrate aspects, the vertical resolution in places where there might be strong gradients. And then there's also this continuous isopycnal coordinate that actually is kind of the analogous ALE representation of this layered isopycnal mode that Gold was originally based on. When we're talking about regional ocean modeling in particular, right, this becomes a very multi-dimensional problem. But like, there is no optimal coordinate, and there is likely not an optimal configuration. It's all balancing on. There is probably some Pareto front where you're balancing a lot of these different things, right? So there's this. Do you want to compare to an existing configuration, right? It's like we have ROMS models for the Arctic. We have ROMS models for inland seas. Do we want to try to compare the output if we're trying to move over to MOM6 for that? Maybe you just choose the choice of that and just say, like, let's just do the preliminary pass and see if we can get the best, make the comparison easier. Do we really care about capturing boundary layer processes? And so this might be something where you might actually want to have a more sigma-like coordinate, right? Especially for something like the benthic bottom layer, right? If you're a biogeochemist and you really want to know what all those guys are doing down there, like, you might actually want a better representation near the bottom. Or if you're someone who really cares about the surface boundary layer processes, then maybe that's just saying that you want a Z coordinate with very fine resolution up there. How do you resolve this weak stratification, right? If you have a place where you have a set of isopycnal coordinates and there really are not actually sufficient resolution to capture very weak stratification, you're going to kind of just mix away a lot of your internal stuff. And an aspect of the fact that these layers can vanish also means that you're potentially wasting some vertical resolution, right? So if you have, an isopycnal model with 50 layers, but 40 of those isopycnals never exist, you're effectively running with a model that only has 10 layers, which is not a good use of anyone's time, really. Open boundary conditions, right? So if you're taking output from a different GCM or from a couple climate model or something like that, and it's only on a particular set of coordinates, like a Z coordinate, let's say, then you have to figure out how you can best match that onto the coordinate of your original model. You can use a lot of this regrid remapping techniques to actually do that, right? So transfer from Z to whatever the state and the grid of the model is. But you will still be incurring some small error by doing that regrid remap. And then there's a lot of invisible assumptions, right, that people kind of just take for granted sometimes, where it's like, oh yes, my model is always Z. So, two examples that came to my mind was, you use the Arctic Ocean with default HICOM, right? Okay, great. You waste some isosignals because they don't exist. The surface Z spacing doesn't necessarily resolve the thin boundary layer structure. And so, whereas you were like, oh, it was good enough for the global model, but maybe you actually need to do that because you need better resolution in the top 20 meters instead of potentially down to the top 100 meters or 200 meters or thousands of meters. Puget Sound with the Z coordinate, how do you assure that the bottom boundary is resolved everywhere in that case? Right. Again, you're potentially throwing away layers because you're going from, an average depth of maybe 150 meters, but you still need to account for those deep channels, which might go down to 400 or 500 meters. And then, kind of the last thing here, there's just, again, I might just skip this slide just to make sure we get to questions. But there are also aspects where we use this regrid remap technology to do things in the model itself that are outside of this vertical kind of transport and remapping of the layers. There's two schemes in particular. They're both the diffusion related ones. One that Gustavo worked on and one that I worked on that essentially says, can we compute fluxes in a different coordinate system that's more natural for the process at hand? And then essentially apply those fluxes back to the native one. So that avoids a full regrid remap step, but still retains our ability to do some of these calculations. Model diagnostics is actually probably the biggest place where we do this. So MOM6 allows you to output diagnostics onto any diagnostic coordinate you want. And so the regrid remap technology is also used for that. There's a lot of caveats in them, especially if you're trying to close budgets in 3D. Keith and I and Steve Riffies and Alistair and Bob think we have the problem corralled, but it's coming down to kind of a software engineering problem in the state. And so, just want to summarize. So big takeaways, MOM6 is a general vertical coordinate model. There's these two modes, the layered isopaginal and the ALE mode. The choice and configuration is something that you really need to consider. So it's not just saying I want a segment coordinate model or I want a hybrid coordinate model, but it's also taking a look at what the configuration of that is. And again, there's all sorts of considerations. It's a multi-parameter optimization problem for a lot of things. And so that's a real challenge when you're working and coming up with a new model, whether it's regional, whether it's global, whether it's idealized. Real thing. If you don't think of anything, if you didn't get anything else out of this, just never assume that the grid is a particular coordinate, please. It will make your life terrible. You will find all these edge cases where that's not the case and where all these hidden assumptions kind of come into play. For developers of new methods, so if you're thinking about developing new parameterization, whether it's a coastal process, whether it's a regional process, whether it's biogeochemical or physical, we have to assume that the underlying constraint is that's general vertical coordinate, and it has to be robust to these vanishing late thin layers that can pop in into out existence time step to time step. There's been a number of advances since OM4. There's a lot more options for remapping schemes. A lot of that was actually, is motivated by trying to take some ideas and learnings and comparisons to HICOM. Alistair did a huge refactor of the reconstruction code itself. So it's actually a little bit easier to see. It's a bit more object oriented. There's been some exploration of alternate vertical coordinates. And then I know that there's some folks who are coming to come up with these offline scripts for examining the configuration of the HICOM line coordinates. So please reach out to folks if you're going to kind of start going to this foray, because there's a lot of work that's been done that could help you kind of get up to speed a little bit faster. And then lastly, this slide again for reference, there's some key aspects of both the code and the documentation, and then published papers that kind of go into a lot of this into much greater depth if people have curiosity about that. And with that, yeah, hopefully that gave you a pretty good overview, and I'm happy to take questions in the last 5 minutes.
Awesome. Thank you, Andrew, for going over one of the characteristic features of MOM6. So we have time for questions.
Hi, so currently I use terrain following coordinates for my work that I'm particularly looking at mixed layer depth. And since I'm using terrain following coordinates at deeper depths, that means it's going to resolve the mixed layer less well. Should I maybe consider using like a Z coordinate system sort of thing instead of that?
Yeah, so I mean, you would have to come up with, someone correct me if I'm wrong, but in this particular case, essentially, if you wanted to do something that was like Z-like near the surface to guarantee that you had like specific resolution of the surface, you could come up with your grid generator that essentially does that, right? Where it's Z-like near the surface and then transitions to sigma below some given depth level. That's all possible within it. It requires a little bit of kind of Frankensteining some of the grid generators together as it stands right now. But it should actually be it's a relatively easy thing to do, quote unquote, but is entirely consistent with the way that MOM6's ALE scheme is actually done. So the part of the code that you wanted to look at if you wanted to create that type of grid generator would be to start in the MOM regridding section.
Okay, thank you. Next question.
Thanks for the talk. Can you explain how outcropping and wetting work for each of these coordinate choices?
I'm sorry, how outcropping?
Outcropping and wetting.
Oh, okay, yeah. So let's see, what's the best way to do this? Maybe it's to go back all the way to this one. Okay, well, let me try to just jump straight back to this. Okay, so what you're kind of sort of potentially talking about is mainly something for the outcropping aspect of it, primarily is a concern for the isopycnal and the hybrid coordinate. So if the isopycnal coordinate, there's no, the only one that's really good, that the layered isopycnal mode is the one that's the most appropriate to use for anything like, a realistic regional domain. And mainly the reason for that is because that actually does have a bulk mixed layer formulation that allows the isopycnic interior to outcrop into that bulk mixed layer and transfer, momentum and tracer and stuff like that from this variable density mixed layer into the interior. So that's the layered isopycnal mode. So that's essentially the way that gold works and works. Now, even though we have a continuous isopycnal version of MOM6, where it is isopycnic material and takes advantage of this ALE stuff, there is no way I think that we've coupled that bulk mixed layer model into the interior. So it's it would be pretty challenging to use that for a more realistic kind of configuration. Now, for the HiCom coordinate, you can read the original black paper, but the way that particularly works is that you essentially define for every layer, you essentially define both an isopycnal level that you want to match. So let's say you really care about 26.2, and then you also specify a minimum outcrop area or minimum outcrop depth. So you would say something like, okay, where would 26.2 exist in this water column? Okay, does it exist there? And is it greater than the minimum depth or not? If it's less than the minimum depth, then you just set it as essentially to that minimum depth. So in that particular way, you get a water column that is Z-like near the surface, but then transitions to the isopycnic interior on the same layer, right? So if you go from this place where that outcrop depth is 100, must be at least 100 meters or something like that, then it will only transition into an isopycnic interior below that depth. So that's one of the things that you're kind of tuning. And so the way to kind of take a look at whether this works or not is to take advantage of some of these scripts that people have run or have written to say, like, if I change some of these parameters, some of these tunings, the isopycnal levels and the outcrop depth, what do I actually end up seeing, and how does that actually look and transform my initial state, let's say, of the model?
All right, time for one more question before we wrap up. Is it?
Are the tracer fluxes also interpolated more or less the same way in the vertical?
So the trace, can you specify what you mean by either the prognostic one or the diagnostic fluxes?
The prognostic one.
So the prognostic fluxes are purely calculated along layer, right? So like if unless you're doing something like a vertical flux because of the boundary layers, like this water mass or this water transfer, right? The tracer fluxes are horizontal. So the tracer fluxes go along the layer itself, right? So just regardless of whether your target grid is a particular thing, we're not recasting the tracer fluxes into a z-like coordinate in the prognostic model itself. Okay, we're just assuming that all horizontal processes happen along a layer. Does that answer your question?
Yes.
Yeah.
All right, well, let's thank Andrew one more time.
Thank you.